Hi, this is John Whitaker, and this is our 5th video lecture for the Probability 1 class. And last time we ended with the fact about the variance formula is what we proved about what the variance is equal to for a discrete random variable. And what I want to do today is start talking about some specific common discrete random variables. And I want to start off with what some people consider to be the simplest discrete random variable. That's a common type, and that's a Bernoulli random variable. So here's the definition. Well, a Bernoulli experiment is an experiment in which there are only two outcomes, possible outcomes, namely success and failure. Okay. Where the probability of success is equal to little p. And so as a definition, if we have, so given a Bernoulli experiment, a Bernoulli random variable is a random variable x defined by x of success equals to 1, and x of a failure equals to 0. That's a Bernoulli random variable. And then the things that we're going to be interested for these discrete random variables are what are their probability mass functions, what's their expected value, what's their variance. And so as a fact, if x is a Bernoulli random variable, then the probability mass function, PMF, of x is f of x, it's right here, and it's defined by p to the x times 1 minus p, which is the chance of failure, to the 1 minus x, where x can be equal to 0 or 1. Okay? So the output values for big X are either 0 or 1. And that's the probability mass function. And that makes sense. If somebody says, what's f of 0? Well, what f of 0 is the chance that you got a failure. And the chance that you got a failure is 1 minus p. And if you let x be 0, this is 1. If you let x be 0, 1 minus x is 1, so you have 1 minus p to 1, that's 1 minus p. For success, that's when x is equal to 1, so f of 1 is the chance of success. That's p to the 1 times 1 minus p to the 1 minus 1. That's 1 minus p to the 0. That's just 1. And then p to the 1 is p. So the chance of success is p, and that's what it is. by the definition of a Bernoulli experiment. Okay, that's good. Remember that when we take a TMF and we sum it up for discrete random variable over all its possible output values, so here this would be x equal, so I guess I'm saying no, that for x equals 0 to 1 of f of x, what we get is, we get the sum as x runs from 0 to 1 of p to the x 1 minus p to the 1 minus x, which would be equal to, let's see, this would be p to the 0, 1 minus p to the 1 plus p to the 1 times 1 minus p to the 0, and then that would be equal to 1 minus p, what this expression would be, and then this term becomes plus p, and that's 1. And that's what we want the sum of all the output values, f of all the output values of x to be equal to. Okay? It's one of the properties of a probability mass function. That sum's going to be equal to 1. The next thing that I want to look at is the expected value of x. So, in fact, if x is Bernoulli, then the expected value of x is equal to p. Let's check that out. So, proof of this is note the expected value of x is equal to the sum as x runs from 0 to 1 of x times f of x, because that's the definition of the expected value of x. And so we're going to have the sum of two terms. The first term is going to be 0 times f of 0, plus this is going to be 1 times f of 1. And that's going to be, well, 0 times something is 0. So this is 0 plus 1 times what f of 1 is. Don't forget, it's p to the 1 times 1 minus p to the 1 minus 1. And so that ends up just being p. That's what we said it's going to be. So that's the proof of that fact. Next thing I want to look at is the variance of x. And so, as a fact, if x is Bernoulli, then the variance of x is equal to p times 1 minus p. And let's prove this. Proof. So the variance of x as a formula, let's don't forget that's what we proved last time, is the expected value of x squared minus the expected value of x to b squared. And so here this is equal to, well, we need to figure out what the expected value of x squared is. So note the expected value of x squared, what that's going to be equal to is, it's an expected value of g of x. So here we write down the sum as x runs from 0 to 1 of g of x, which is equal to x squared, times f of x, the PMF. And so computing that, we get that this is equal to, well, it would be 0 squared times f of 0 plus 1 squared times f of 1. And of course, 0 times something is 0, and then 1 squared is 1, so it's just f of 1, which we know would be p. So the variance of x for being Bernoulli is equal to p minus, and then it's the expected value of x, all that to be squared. Remember, this was the expected value of quantity x squared, which is equal to p minus the expected value of x we found to be p, so that's p squared. That's equal to here. Let's put equal to. And that's equal to p, you factor out p, times 1 minus p, and that's what we said it's going to be. Well, the next thing I want to do is do an example. So as an example, let's say a card is selected from a well-shuffled deck. Define the random variable x by x of a heart is equal to 1, and x of a non-heart is equal to 0. Then we can think of getting a heart as a success and not getting a heart as a failure. And so then x is a Bernoulli random variable. And we say with parameter, that's the p-value. Write this over here. With parameter p equal to 1/4. So that's the chance of success, because that's the chance of getting a heart when you draw one of these cards. Okay, then the PMF is f of x is equal to, well, it would be 1/4 raised to the x times 1 minus 1/4, that's 3/4 raised to the 1 minus x, and don't forget that x is 0 or 1 of those two options. That's the first thing. The second thing is the expected value of x. So that was p. So in this case, that's equal to 1/4. Thirdly, the variance of x, that was equal to p times 1 minus p. So that's 1/4 times 3/4. That's 3/16. So that's the information that we have for this example. And it's a Bernoulli random variable. Okay, the next common discrete random variable we want to talk about is something known as a binomial random variable. So here's its definition. Suppose a Bernoulli experiment is performed in independent times. Let x count the number of successes within these n trials, these n experiments. Then X is a binomial random variable and sometimes we say with parameters, so the thing to change it are n, the number of trials that we have, and p, which is the probability of success, which can change. Okay, so next we want to look at what is the probability mass function for this binomial. So as a fact, the probability let's back up. Let's say this. Let X be a binomial random variable with parameters n and p. Then the P and F of X is, so it's F of X is equal to, so here it's n, choose X, p to the x, 1 minus p to the n minus x, and where x can be equal to, so let's recall, what does x do? It counts the number of successes that you had in the n trials. You did this experiment n times. You say, well, how many times did we get a success? Well, the least amount of times you could have got a success was 0. Not have ever got a success. And could have gotten 1 success, 2 success, but the most number of successes you could have had if you did it n times is n. Maybe you had a success every time. And why does it make sense that this function gives the probability that big X is equal to X? So here's what we're thinking. If you want to have X number of successes, so we think of maybe having trials, n trials, so I'm going to have a dash, this first dash for the first trial's outcome, second dash for the second trial's outcome, third dash, up to n dashes, okay? I got these n dashes here, whatever that is. So here I happen to have made 7 dashes, let's say n was 7. If you said, well, what's the chance that I had 3, let's say, successes? So the first thing that you'd have to do is you'd say, well, where did the 3 successes occur? So maybe they occurred success here, success here, success here, first 3. And the rest of them would have been failure. So there's lots of ways that I could have within these 7 slots, 3 of them be successes. And as a matter of fact, there are 7 choose 3. So you say, which slots did we have success? Which trials did we have success on? And so that's a choosing. So, and the reason we use combinations here is because if I said I had success in the first trial, second trial, and the third trial, that's the same thing as saying I had success in the third trial, second trial, first trial. Okay, so that's the number of ways in which we could place the successes that we got. Then when you say, well, if I had success, 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 failure, 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 well, what's the chance I got a success here? Well, it would be P. What's the chance I got a success here? P. What's the chance I got a success here? P. So that would be, they're independent events. So we have P raised to the 3, or X here. And then 1 minus P are the probabilities of failures in each one of these independent activities. And you'd have 1 minus P times itself 4 times, or general, would be N minus X. So that's why the probability mass function is what it is. Okay, the next thing I want to look at is why is this probability mass function, if you sum it up over the output values, why is that going to be equal to 1? And that's based on a fact called the Binomial Theorem, which is why this particular random variable has the name that it does. Okay, so let me write up the Binomial Theorem. So this is a recall. The Binomial Theorem says, hey, if you got quantities, x plus y, and raise them to the n, that's equal to the sum as k runs from 0 to n of n choose k, and then this would be x to the k, y to the n minus k. That's what it says. So you can try this out with x and y's raised to different natural numbers here. N represents a natural number. 1, you'll see the form is true. 7, you'll see the form is true. 3, you'll see the form is true. And this binomial theorem is proven by induction. All right, but using that, note that the sum, here let me start off by saying, note if f of x is the PMF of a binomial random variable, x, then the sum as x runs from 0 to n of f of x would be equal to, so this is the sum over all the output values we get for the binomial random variable, is equal to the sum as x runs from 0 to n of, well, this was n, choose x, p to the x, 1 minus p to the n minus x. Now this fits perfectly with the right-hand side of the binomial theorem, where our index is x instead of k. If this is n, choose the index, p to the index, x to the index, 1 minus p, that's the y, to the upper part of the sum minus the index that runs. So it fits perfectly. And so here, the role of x in our formula for binomial random variable is being played by p, and the role of y is being played by 1 minus p. So the answer here is 1 plus 1 minus p. I'm sorry, it's not 1, it's p, plus 1 minus p, raised to the n. And so that ends up being 1 to the n, and that's just 1. So that's how the sum of the PMF is equal to 1. Well, let's look at the expected value. If x is a binomial random variable, with parameters n and p, then the expected value of x is equal to np. Before I go any further, let me just say that a Bernoulli random variable is a binomial random variable where you only have one trial. You only did the experiment once. And if you remember, the expected value of a Bernoulli was just equal to p. So that's when n is 1. You have 1 times p, that's p. Let's prove this fact. We'll let x be binomial with parameters n and p. Then the expected value of x, well, it's the sum as x runs from 0 to n of x times f of x, which will be equal to the sum as x runs from 0 to n of x times n choose x, p to the x, 1 minus p to the n minus x. And then this is equal to, well, first of all, when you let x be 0, you get 0 times something. So the first term of the sum is going to be 0. So that's one not included. So let's have x running from 1 to n of x over n choose x, p to the x, 1 minus p to the n minus x. Okay. All right, so this is equal to the sum as x runs from 1 to n, that's an n. Here, this is x, and at n choose x combination. It's going to be n factorial over n minus x factorial times x factorial. Here's p to the x, 1 minus p to the n minus x. And this x and this x factorial will cancel. And so we're left with the sum as x runs from 1 to n of n factorial over n minus x factorial x minus 1. Okay? And then if we pull out a p, then this will be p to the x minus 1, and then this is 1 minus p to the n minus x. I forgot a factorial at the bottom. Okay, that's great. We can also pull out an n, so let's do that. So we have x running from 1 to n. This will be n minus 1. Over n minus 1 times, if you want, or minus x minus 1, factorial, over x minus 1 factorial. This is p to the, this is n minus 1 factorial, let's take a lot for it. X minus 1, 1 minus p to the n, and you can rewrite this as n minus 1 minus x minus 1. That's what we have. Okay. This is equal to, here, this is np still, so we've taken out an n as well as p. Sum as x runs from 1 to infinity. This n minus 1 factorial over n minus 1 minus the quantity x minus 1 factorial over x minus 1 factorial. That's nothing more than n minus 1. This shouldn't be infinity, it should be n. N minus 1, choose x minus 1. Okay. This is p to the x minus 1, 1 minus p to the n minus 1 minus the quantity x minus 1. Okay, here we're going to make a change in the sum. I'm going to let k be equal to x minus 1. So our sum then was n times p, but k is 1 less than whatever x was. So the sum will go from, well, x started at 1, so now k will start at 0. And x went all the way to n, k will go to 1 less than that, n minus 1. And then it said n minus 1, okay, that stays the same. And then it said x minus 1, but x minus 1 is the same thing as k, so choose k. Then it said p, previously said x minus 1, but that just be p to k. And then it's times 1 minus p to the n minus 1, and then minus the point of x minus 1, that'd be minus k. Okay, this, using the binomial theorem, is np, and this fits the binomial theorem perfectly. And so here we don't run up to n, we run up to n minus 1, but everything else works identically. And so what we get is, this is p plus 1 minus p raised to n minus 1. And that's just 1, so it's n times p times 1 to the n minus 1. And so that's n times p. It occurs to me, that ends the proof, but it occurs to me, the one thing that I haven't said, that I should have said probably earlier, is as a notational fact or convention, when we're doing factorials, 0 factorials find to be 1. So that's something we need to keep in mind for our work. Okay, well, we've got the expected value of the binomial. Let's see if we can get the variance of the binomial. Okay. So as a definition, if we let x be a binomial with parameters n and p, then the variance of x is equal to n times p times 1 minus p. I want you to remember that the variance for Bernoulli was p times 1 minus p. So this n was equal to 1 for the binomial case to generate the Bernoulli. This is not a definition, this is a fact. And that's something we want to prove, okay? I'm sorry about that comment definition. So let's do this proof. Okay, so first of all, we're going to let x be binomial with parameter n and p, and then the variance of x, let's don't forget my formula, is the expected value of x squared minus the expected value of x to b squared. So we need to know, we know what the expected value of x is, that we can square it, but we don't know what the expected value of x squared. So let's look at it. Well, that's equal to the sum as x runs from 0 to n of x squared, and then this would be f of x, which equals to the sum as x runs from 0 to n of x squared times n, choose x, p to the x, 1 minus p to the n minus x. Okay. Again, when x is equal to 0, the first term of the sum would be 0, so there's no use including that. So this is the sum as x runs from 1 to n of x squared, n choose x, which I'll rewrite as n factorial over n minus x factorial, and here's x factorial. And then this is p to the x, 1 minus p to the n minus x. And then we can cancel out one of these x's with an x that's in the bottom, and we get a sum as x runs from 1 to n of x, n factorial, n minus x factorial. This will be x minus 1 factorial, p to the x, 1 minus p to the n minus x. Excuse me. Now, if we take out an np, and I can do that because they don't depend on x. So take out an np again. And x runs from 1 to n of x, and here the n minus 1 factorial. I'll rewrite the bottom here as n minus 1 times x minus 1 factorial, so those are exactly the same. And then here's x minus 1 factorial. I've taken out a p, so this is p to the x minus 1. And here this is 1 minus p, and I'm still going to leave that to the n minus x. And then we notice that this fraction can be rewritten as np times the sum as x runs from 1 to n of x. This is n minus 1, choose x minus 1, as we had before. P to the x minus 1, 1 minus p to the n minus x. Okay, here's what we're going to do next. We're going to make a substitution for the index. Again, we're going to let k be equal to x minus 1. And so this is equal to n times p times the sum. So x had started from 1 to n. So here k is going to go from 0 to n minus 1. And then there's an x that starts off with. Well, x is equal to k plus 1. So it's k plus 1. X is equal to k plus 1. Just solve for x right there. And then it would be times n minus 1 choose x minus 1, but x minus 1 is k. This would be p to the x minus 1 is what it has, so it would be p to k. And then this is 1 minus p. This would be n, it was n minus x. So this is n minus the quantity k plus 1. This is a sum np. I'm sorry, it's np times the sum as k runs from 0 to n minus 1. I'm going to make one little change here. It's k plus 1. Forgive me for writing so much for such a small change. The only thing I want to change here is this is 1 minus p to n minus 1 minus k. So here, this is np times two sums. So I'll rewrite this. A sum is k runs from 0 to n minus 1 of k times n minus 1 choose k, p to the k, 1 minus p to the n minus 1 minus k, plus the sum as k runs from 0 to n minus 1 of 1 times this, which is just n minus 1 choose k, p to the k, 1 minus p to the, it's n minus 1 minus k. Let's see if that's what it is. Okay, that's what we're. And this is equal to np. Now, when we look at this first sum, it is nothing more than the expected value of a Bernoulli random variable, okay, whose parameters are p and n minus 1. It's exactly the right form for that expected value. And so here, what I would get is this will be n minus 1 times p, because that's what the expected value would be. Plus, here, this fits the binomial theorem perfectly, or you could think of it as being the p and f for a binomial random variable with parameters n minus 1 and p. And so it ends up, the sum of it is equal to, the sum of that p and f is 1. And so here's what we're getting. We're getting np times np minus p plus 1, which is equal to n squared p squared minus np squared plus np. Plus np. Okay. So that's the expected value of x squared. So we're still calculating the variance. So the variance of x is going to be equal to the expected value of x squared minus the expected value of x to b squared, and that is equal to what we just found, which was n squared p squared minus np squared plus np minus, this guy was np to b squared. So this np to b squared and n squared p squared, they're the same except they have opposite signs. So you get minus, I'll rewrite this term first. You get np minus np squared. You take out an np, and you have 1 minus p, and that's exactly what we said it was going to be. So that concludes that proof. The next thing I'd like to do is an example. So let's look at similar to the previous example we had. Let's say a card is selected at random from a standard deck. Its suit is noted, and the card is returned to the deck and reshuffled. And deck reshuffled. Let's say this process is done 5 times. Okay, and someone says, count the, let x count the number of hearts drawn in these 5 trials. then that tells us that x is binomial with parameters five and 1/4, so that's the p-value. This is the n-value. Okay. The PMF, its f of x is equal to, well, it'll be 5, choose x, p to the x, so p is 1/4. And then 1 minus p, that's 3/4 to the 5 minus x, and x can be equal to 0, 1, all the way up to 5. The expected value of x is equal to np, which in this case is 5 times 1/4, 5/4. And the variance of x, which is equal to np times 1 minus p, is equal to 5 times 1/4 times 3/4. So that's 15 over 16. That's an example of a binomial random variable. I would like to get started just from the next random variable, just to get it up, the common discrete random variable. And so here's the definition. A Poisson random variable is a random variable x, is a discrete random variable x, x whose PMF, probability mass function, is given by f of x is equal to e to the minus lambda, lambda to the x all over x factorial, where lambda is some fixed number that's greater than 0 that is associated to this random variable x. So really this random variable is defined by having this PMF. I forgot something. I forgot what the x's can run from. The x's can be 0, 1, 2, well, they go forever. So in this case, x is Poisson with parameter lambda. And let me do one thing. Here is a recall, and this is something that we see in calculus 2, and it has to do with Taylor's theorem, is that by Taylor's theorem, we have a power series representation for e to the x is equal to the sum as n runs from 0 to infinity of x to the n over n factorial. And this helps us in terms of showing that the sum of the PMF values as x runs from 0 to infinity of f of x equaling for a Poisson sum x runs from 0 to infinity of e to the minus lambda, lambda to the x over x factorial. Here we have 0 factorial involved. Remember, that's 1. This is equal to e to the minus lambda can be pulled out of the sum because it does not depend on the x, the index. And here's lambda to the x over x factorial. And this sum fits perfectly with this expression here. Okay, just the index here is n equals 0, the index there is x equals 0, and x here is being played by lambda. So this is equal to, by this Taylor's theorem, is e to the minus lambda, and then this is e to the x is being played by lambda, and e to the minus lambda times e to the lambda, you add the exponents, you get e to the 0, and that's 1. And remember, the sum of the PMF over all possible x values that the random variable can take should be equal to 1, and it does in this case. Okay. We'll continue next time by studying some more of the attributes and examples of a Poisson random variable. Thank you very much.